Good morning, ladies and gentlemen, this is Capandball here, and we are flying back in time to the 17th century. We are flying back to the year 1664 to the age of matchlock muskets and wheel-lock pistols. Well, this is a kind of experimental archaeology project that I'm involved in at the university. We have been researching the muzzle velocity of various 17th century firearms for a long time now. Our university research team is exploring the ruins of Zrínyi Újvár, or as it is in English, the new fort of Nikola Zrinski. Nikola Zrinski, or Zrínyi Miklós, is the hero of the Croatian and the Hungarian nation as well. It's a really good connection between these two beautiful countries. This little fort was built at the conjunction of the river Drava and the Mura at the southern border of the city, and Zrinski used this fort to be as a military base for his raids against the Ottoman Empire. It was a kind of a bridgehead. This is a crucial location as most of the trade routes and the military routes were leading through this area in the direction of Styria, part of the Habsburg Empire, and from Styria to the direction of Vienna. But before we carry on, let me thank you for your support. Your donation through Patreon, or buying our authentic American Civil War cartridge boxes, or percussion revolver cartridge formers, or US Arsenal Stadia rangefinders, or powder measure leathers, authentic powder measure leathers, or flintlock tools. They are also very authentic. And also our rubber printing plates for Arsenal cartridge bundles. They all help to keep the quality of our channel high. Without you, this would be much difficult. This little fort, actually a little earthen fort, was built in 1661 and it was ruined in 1664, and it was never rebuilt. It was ruined by the Ottoman army in June 1664. And other than this siege, there is no known engagement for this little fort. It was never rebuilt, as I told you, which means that this little fort is a true time capsule. We have hundreds of bullets recovered from this site that help us to better understand the ballistics of the 17th century musket. It offers a very unique method, a very unique way to get a clear picture about the muzzle velocity of the bullet, which is the most important data we need for ballistics reproduction. So we are going to get a clear picture about the two-lot musket ball now. According to Raimondo Montecuccoli, the two-lot musket had a bore of 14 to the pound that corresponds to circa 17.9 millimeters. It was loaded with a 16-gauge ball that is 17.1 millimeters, using one of the most common units for firearms calibers, the Nürnberger silver pound of 477 grams. So the windage between the bore and the ball was 0.8 millimeters. These matchlock muskets had a barrel length of 1 meter and a weight of 4.5 to 5 kilograms. They could be fired from a fork or without a fork as well. The soldier could use the wooden containers on the bandolier for loading the musket, or he could also use paper cartridges, holding the powder charge and the ball together. According to Montecuccoli, a soldier needed 16 rounds for a day. Knowing the caliber of the musket, the size of the ball, and the muzzle velocity of the ball are the three most important points in understanding the external ballistics. If you miss one of these points, then you won't arrive to a proper solution for sure. We have many written sources about the proper size of the bore and proper size of the bullet. For example, Raimondo Montecuccoli, who was the commander of the Emperor's army in 1664, states the following: for a musket with a bore size of 14 to the pound needs a bullet that is 16 to the pound for proper and easy loading. So actually there are two calibers to understand in the case of the 17th century musket. One is the Laufkaliber, as it was called in German, or the bore caliber, and the second one is the Rollkaliber, or the bullet caliber. They are different. The large windage between barrel and bullet had two main reasons. The first one was the small bullet was easy to load even into the full barrel. Second, the difference between the ball and the barrel ensured that If there were no military standards, by the way, in the 17th century there were no exact military standards for the musket, which means that in the bore sizes there could be slight differences. But with a much smaller bore, it was always easy to load it. So there was no logistics problem in supplying bullets to the army, if the bullet was small enough to be fired from any musket bores. We also have proper information about the charge of the musket. Raimondo Montecuccoli says that from good quality black powder, you need half of the bullet weight, and from bad quality powder, you need 3/4 of the bullet weight. And we also know the composition and the making method of these powders. We could even mix this powder according to the contemporary manuals. This can be an option, but there is a huge problem, because the pureness of the ingredients will affect the power of the powder, and they are very, very hard to replicate. Especially the quality of the salpeter, the coal, they were very important. So even if I know the mixing ratio, I know the production method, it is still not sure that I'm going to arrive to the 17th century powder quality. Why? Because there is no standard 17th century powder quality. This is why they had eprouvettes at the units that they use for testing the power of each and every single batch of black powder. Here is the powder proofing machine of Josef Furtenbach, a mathematician from Ulm, that he designed in 1626 and was used by the Imperial Army. The device was 63 cm high with a small mortar at the bottom and a weight that could be stopped at different heights. The more power the powder had, the higher it moved the weight on the scale. So what happens if you just use the 17th century load data and charge your musket with modern powders? Well, the problem here is that the modern powders are much different from the 17th century powders. Even if the granulation is the same, and even if the mixing ratio is the same, there is one important step in the production method that was missing in the 17th century, and this is the compression of the cakes, which means that the modern powders are heavier and are much, much stronger than the old powders. The best thing would be to find contemporary information about the muzzle velocity of the musket. But the problem is that Benjamin Robins, an English mathematician, only invented the ballistic pendulum for measuring the velocity of a projectile in 1742. So how can we get a clear picture about the muzzle velocity of a 17th century musket? There are different good and not so good approaches in this case. The first one is connected to Austria, Graz, the Landeszeughaus. It's a beautiful collection of 16th and 17th century arms. If you have a chance, go there, it's impressive. Peter Kren and his crew created the basics for researching the ballistic capabilities of historical firearms, and we have to be very, very grateful to them for this. They used original muskets and original bullet molds. The problem with their experiment is using modern powder. They used 3FG granulation German Jagdschwarzpulver, which is a fine powder. They used a load ratio of 1/3 of the bullet weight, which means that the muzzle velocities they received were very, very high. For a musket, well over 450 meters per second. There is also an excellent method described by David P. Miller. He examined bullets collected from the Marston Moor and Edge Hill battlefields and noticed that in many cases there is a bend all around the bullet at the circumference. Well, this bend is caused by the grinding effect of the bore, and it is caused by the gas pressure. As the pure lead bullet receives a kick from the powder charges, the bullet is upset in the bore. So the bullet that was originally heavily undersized is going to fit the bore properly, and it is going to touch the bore all across its circumference. So the bore itself is going to grind a belt into the bullet. When David P. Miller was examining the muzzle velocity and the gas pressure that was needed to recreate this effect, he recognized that he needs well over 400 meters per second of velocities to reach this. The problem with this method is that it is dependent on the windage between the bullet and the bore. If the windage is big, then the grinding effect is less. If the windage is small, then the grinding effect will be stronger. Well, here is the method that we developed based on the bullets we recovered from the site at Zrínyi-Újvár. Well, these bullets seem to offer us a much more accurate way to determine the muzzle velocity. We have many lead bullets that were fired from the curtain of the fort, the wall of the fort, into a besieging trench nearby. These are all musket balls, Christian musket balls, as they were going into the direction of the Ottoman army. And they impacted sand, pure sand, which means that the bullets could expand very symmetrically, like this one. The method itself is very, very easy, logic, and very simple. First, we can recreate the impact velocity of this projectile. It is pure lead. So if we can reach the same kind of deformity, then we have the same impact velocity. Second, measure the distance between the trench where it impacted and between the wall where the firing point was. Third, knowing the impact velocity, knowing the range, and knowing the ballistic coefficient of the lead round ball, we can arrive to the muzzle velocity. Simple, isn't it? And the key benefit of this method is that it is absolutely not dependent on the quality and quantity of the powder. Let me guide you through the whole process we went through during this 2-year research period. First, we selected 5 musket balls, flattened musket balls from the same location. These are the references. We measured their weight, measured their dimensions, and we also checked their material, and it turned out that they are absolutely pure 99% lead. Second, we selected the right caliber matchlock musket and the right caliber lead round balls, matching Montecuccoli's intentions. But lead round balls do lose a bit of weight upon firing. This is caused by 2 effects. The first one is the grinding effect of the bore. As the bullet is touching the bore, it is grinded. The lead is soft. We cannot do anything about it. The second effect is the cutting effect of the hot gases as they are blowing through the windage between the bore and the bullet. So to determine this weight loss, we used a musket that is matching the Montecuccoli specifications and the lead bullet that is matching the Montecuccoli specifications, and we fired the lead round ball into soft substance. The bullet catcher is a carton box full of loose cotton. It is incredible that it stops the projectile under half a meter. Ha! That's it. There's our bullet. Let's check how much weight it lost. It was interesting to see that the bending effect was not complete around the circumference of the round ball, so the bullet actually did not expand fully in the bore. We measured 5 shots, and it turned out that, in average, the bullets lose 0.6% weight upon firing, so this was a modifier that we used for using this lead round ball as a reference. The weight of this lead round ball was increased by 0.6% to arrive to its original weight, and that was used for calculations. Our third task was to determine the original diameter of this flattened bullet. Well, we know its weight, we know it's pure lead, which means we know its density. We added 0.6% weight due to the weight loss during the firing, and then we calculated the original radius. And from the radius, by doubling it, we can arrive to the original diameter of this bullet. Fourth, we visited the same spot at Zrínyi Újvár, at our original location, and with the permission of the authorities, we carried out live firing tests into the same sand where we recovered this flattened bullet. At this very early point of the experiments, we were still waiting for our 17th century musket reproduction with the exact desired bore caliber, so we carried out these tests shooting with an arquebuse with the required caliber. At this point, the type of arm and the method of loading was not relevant. We only needed to record the impact velocity, providing the required deformity of the bullet.
Ásó is, én tudom, hogy visszakétnek ásókormuk van, de... Még mindig? Akkor most nem dobozja?
Pont ezt akartuk elkerülni a köveket.
Hát akkor... Az előbb is ott volt.
And we started to increase the charge until we reached the deformity that was desired. And this is the result. This is the result. And to reach this deformity that is very, very similar to the original in all dimensions, we needed 246 meters per second impact velocity. Fifth, we continued our test at the shooting range. We used the Ballistics radar to determine the traveling velocity of the bullet at 80 meters. And we started increasing the charge again until we reached that. Oh, sure. And after a few shots, I was very close to the desired velocity. And it turned out, to achieve this, we need 100 grains of 1F Swiss powder, large corn Swiss powder, that is generating 305 meters per second muzzle velocity. And this was the point where we stopped and said, what? This is much lower than in the previous researches. How come? And the case seemed clear, because the impact velocity is good, the bullet is good, the range is good, the musket is good. Then what else? Why it is happening? It is only 305 meters per second, that is 1000 feet per sec. And all the other data were above 400 meters per second. So it was indeed a strange number. But the muzzle velocity, let's not forget, it is very, very important, because it is determining the external ballistics and the terminal ballistics, which means it has a huge impact on infantry firearms tactics. Let's see now the performance of our charge with our musket. Let's start with the accuracy, first at 50 meters. The musket here is loaded with 100 grains of 1FG Swiss powder, tissue paper as wedding, and a 17.1 mm lead round ball.
Látsz valamit?
And that is, ladies and gentlemen, 5 shots at 50 meters with a periodically correct charge according to Zrínyi. The size of the group is a bit larger than the head size group, but we are well in the chest of an enemy soldier, which means that we can move up to 80 meters and check the actual distance. But let's check now the accuracy at 80 meters. This is the distance between the trench and between the wall of the fort. So ladies and gentlemen, this is the 80-meter target, and out of the 5 shots I have only 1, 2, 3 in the target. And also I have a miss here. I nearly destroyed the target. So this technically means that from this distance, well, you have the chance to miss the enemy single soldier. So probably this was a distance where you were better switching to shooting on enemy close combat formation. But it was a fun experiment. And I really have to say that probably this is the closest you can get today to the original muzzle velocity and to the original accuracy of the musket. So, accuracy is only one data regarding ballistics. It is also very important to understand the ballistic curve of the bullet. Let's check it now. On this graph you can see the flight of the bullet compared to the line of sight. I designated a vital area 50 cm above and below the line of sight as the upper body of a human. According to this graph, the projectile falls very fast. At 140 meters it exits the vital zone, and at 170 meters it hits the ground. Don't forget that the infantry manuals of the 17th century lacked instructions for aiming to larger distances, and these muskets did not have an adjustable rear sight. This next graph shows the drop of energy and velocity as the bullet is flying downrange. The simulation also revealed that with an ideal angle of 29 degrees, the bullet shall fly to a maximum distance of 900 meters. The energy of the bullet drops under 100 joules at 550-570 meters. This could be the outer edge of causing injury to the enemy soldier. If you want to understand the terminal ballistics of a bullet, then you have to use ballistic gelatin. We are going to use Clearview ballistic gelatin to test the effect of this musket ball, and we are going to compare it to a modern military cartridge. It will be a Full Metal Jacket 308 cartridge.
Mehet, uraim?
We simulated the 80-meter impact, and the test showed that the energy transfer of the heavy round ball was not really strong. Even 2 gelatin blocks were not able to stop the bullet, and the temporary cavity caused by the shockwave of the bullet was not significant. And as the entrance wound, it did not close. It's nice round, around 10 to 11 millimeters. And the energy transfer is quite minimal, but the penetration is just excellent. And here is a comparison of the musket ball to the effect of the ball of the wheel-lock pistol fired from point-blank range, as it was advised by the contemporary manuals. Both projectiles penetrated the single block, but the shockwave of the large musket ball was clearly bigger, therefore its destruction is more. This graph shows a temporary and permanent cavity caused by the musket ball redrawn from the slow motion video. Full penetration of the 2 40 cm gelatin blocks and the moderate energy transfer it shows, but the entrance wound is strong and the central cavity marked with red is also significant. This is the same kind of graph showing the terminal effect of the 308 Full Metal Jacket bullet at the same 80-meter distance. A larger impact velocity and energy created a stronger shockwave. The bullet turned in the wound as it slowed down and lost its jacket. Both the lead core and the jacket stopped in the second gelatin block. While the entrance wound was much smaller than in the case of the musket ball, every other terminal ballistic effect were much stronger. And now it is time for some practical, tactical accuracy. We are going to fire the musket from the fork, and for the first time we are going to charge it from the little wooden containers on the bandolier, and later we are going to charge it from paper cartridges as it was done before. Both ways were used in the 17th century. Now I am replicating the original loading sequence of the drills, so priming is the first step. Today it is not considered safe, so please do not follow this procedure during your shooting sessions.
Nem, mögöttem, Léci. Mögöttem. Mögöttem. So ladies and gentlemen, and this is 50 meters shot from the fork. 5 shots are, let's say, within a 20 centimeter group, which is quite good, which is exactly better than what I shot from the rest. Which means that shooting from the fork and shooting with the original loading procedure, well, quite close to the original loading procedure, according to the early 17th century drills, is just as good as shooting from the rest. So, yeah, that's not bad. That's not bad. Not bad at all.
And now it is time to shoot the musket with paper cartridges, rolled according to the instructions of John Crusoe.
And this is a 50-meter group with early cartridges, and I really have to say that the group is quite similar. It's I have a flyer here, but technically the group is the same 20 centimeter as with the other loading method. But the procedure was faster. It was surely faster, so that's a good proof that the cartridge is a more modern stuff in shooting. But otherwise, there is not too much difference between the ballistics of the two loading methods.
So does this mean that all the musket balls in the 17th century were fired with the same low muzzle velocities? I'm not sure about it. Even if nearly all the musket balls recovered from the Zrínyi-Újvár research area, they show the signs of low gas pressure and low muzzle velocities, it does not mean that everybody else is wrong in this question.
Here is a brief comparison of few of the most important researches mentioning the muzzle velocity of 17th century musket balls. Adding the projectiles of Zrínyi-Újvár probably will add a bit more information to the picture about 17th century firearms tactics, and also to the history of the War of 1664 between the Habsburg and Ottoman Empire.
Probably this low velocity is only valid for this engagement. We know that the Habsburg army during the War of 1664 against the Ottoman Empire was short on powder, so probably this is the reason for the lower velocities and the lower gas pressures. But I really hope that my fellow researchers will be able to use this method when the range between the target and the firing point is available for determining other muzzle velocities all across Europe. Ladies and gentlemen, this complete research will be published later, full in English, in a scientific paper, so be prepared for more information about the bullets of Zrinski. Ladies and gentlemen, until next time, stay cool and keep your powder dry.